Hello everyone.
Well, according to the oil pressure gauge, it's still doing good. I really haven't seen the fuel tank fuel gauge move.
Even after adding 5 gallons to the tank.
I don't see that moving. Let me put the headlights on.
No movement there.
No, I don't see the amp gauge moving. Temperature gauge hasn't come up yet. Who knows if these are working or not?
I'm interested in troubleshooting these gauges, and the temperature gauge is pretty important, so I'll start with that one. I've watched a few videos about this topic. They've been very helpful, but 40 years of technical experience with industrial electronics has me thinking it would be easiest to troubleshoot these classic automotive gauges if I had a dummy load available. What is a dummy load, you might ask? In this case, a dummy load would be a resistor with a fixed value that can be used as a substitute for the variable resistance that's provided by a given sending unit or sensor in a gauge's analog circuitry. I'll be creating some dummy loads to be used as tools in troubleshooting my Mustang's gauge circuits. Dummy loads for this application can easily be made from readily available standard electronic resistors. I'm making my dummy loads from resistors I found in this box of random resistors I've had laying around for the last 30 years. But it's easier with the assortments we have available online now. I think this will be the easiest way to troubleshoot the Mustang's faulty gauge functioning. So I was going to go into a detailed description of how I made my dummy loads and all the Ohm's law math behind this process, and assembling my dummy loads and blah blah blah. I even made all these slides to show you how I did it, but it's mostly overkill that would bore you to death. So I'm skipping a lot of the detailed explanation and getting right to the information I think you're here for. How this system works and how to troubleshoot it when it doesn't. And how I made these dummy loads. So let's move on. Well, our gauge sensors, temperature, oil pressure, and fuel tank level are all variable resistors with a range of 10 ohms to 73 ohms. Their resistance values vary as the level they're monitoring changes. I'm working with the temperature gauge first, so let's stick with that. Note that some of the reference sources for this information are a little different. Some say it's 75 ohms, one source said 77 ohms. These gauges aren't exactly certifiably accurate. They just provide a rough indication, so it doesn't make much difference as long as they're within reason. That's the best we can hope for. Another problem for gauge accuracy is the instrumentation power supply. This little voltage regulator resides on the back of the instrument panel. It provides 6 volts, sort of, using a crude antiquated method. It actually provides a 12-volt pulse at what should be a 50% duty cycle, and it isn't accurately repeatable. More on this later. This diagram shows a basic black box circuit layout. As we can see, the voltage regulator provides power to the gauge, which gets a variable resistance to ground from the temperature sensor. The hotter the engine, the lower the resistance to ground, and the more current flowing through the meter. And as current increases through the meter, the more an internal bimetal distorts its shape and moves the needle. Now we can insert a dummy load. It can be anywhere in the range of 10 ohms to 73 ohms or a little more. Since the sensors have a range from 10 to 73 ohms, I want a 10 ohm dummy resistance, a 73 ohm dummy resistance, and something in the middle. These gauges don't function in a linear fashion, but I've learned through trial and error that 25 ohms puts the gauge indicator needle close to the center of its range of travel. So my dummy loads made out of random resistors I had look like this. But you can make yours like this with one of the available resistor kits. I'd suggest using half-watt resistors with 1% accuracy. This will work fine.
Okay, I've got two lines of resistors here that need to be soldered together, and then they'll be soldered together on the ends. I taped them here just so I could carry them around without losing them. And I measured the resistance on all of them. This is 67.3 ohms, 38.8 ohms, 38.7 ohms, and 1.1 ohm. And taken together in series, they'll be 145.9 ohms. And then on this string, there are 67.5 ohms, 39 ohms, 38.9 ohms, and 1 ohm. Altogether, I think they're going to be 73.08 ohms, which is almost perfect. All right. I'm going to start by just cleaning these little resistor wires with some Scotch-Brite just to take off any contaminants that might be on there, oxidation or whatever, and by adding some from the Scotch-Brite. Okay. Just want to clean them off. Okay. I guess I'll take off a little bit of their length. Twist them together at the center of the wire. Little bit hanging out there.
I'm using rosin core solder. It has soldering flux in its core.
You heat the wire and melt the solder on the hot wire. Then cool it off. Don't want those little resistors getting too hot. And I hooked the ohm meter across the length of those. And it's reading 145.9, yeah, is what I calculated. So it's right on what I wanted.
I soldered the second series string together the same way.
That's 145, 146. These are loose. About 145.8, that says. 145.9. So basically 146, which is what I'm after. Now I'm going to join these two in parallel with each other.
You can see I put shrink tubing on both resistor strings.
Okay, if you remember my goal, it's 73 ohms. So let's see what this thing's reading now. That looks like 73 exactly. 73.1, 73. 73 ohms, that's exactly what I wanted, that's perfect. So now I have a perfect dummy load of 73 ohms for troubleshooting my Mustang's gauge cluster, the gauges in particular, and I'll be looking at the temperature gauge first and the fuel gauge, and I might want to just confirm the oil pressure gauge, because I'm not sure how accurate that is. So that's that. So I've got all kinds of lights down here now, trying to see what's going on here, and I think maybe the camera can even see that this is the temperature sender right here, temperature sensor. It's located behind the distributor, so it's hard to get some light on it, but I got enough light on it so I think we can see it here. I'll be using this metal tag that's bolted to the block as a ground lead connection spot. It's a good ground. Okay, so the black lead here is still clipped to this metal tab. It's a metal tag which is bolted to the intake manifold. And the red lead is clipped to the temperature sensor wire. So I'm going to connect that across this 73 ohm resistor that I made. Make sure it doesn't short out anywhere. I'll just, let's see, I'll set it up here. And we'll take a look at the gauge now in the car and see what it's reading. So that's the gauge on 73 ohms. It's like the needle is just about on the C mark, the lowest mark on the gauge.
This tells me the temperature circuit and voltage regulator are working within reason, and 75 ohms might look better.
Okay, let's replace this 73 ohm resistor with our 10 ohm resistor. I should be referring to them as what they are. That's my 10 ohm dummy load. Now let's see what that looks like on the gauge. So that's all the way up there on the hot mark. And that's what it should be. That's the highest resistance. It should be the hottest temperature.
0 ohms to ground actually pegs the needle off the scale. Don't ask me how I know. I wouldn't recommend doing that. Again, this further confirms the gauge circuit and power source are doing pretty well. Okay, the final dummy load test. I'll remove the 10 ohm resistor and insert the 25 ohm dummy load resistor. Let's see what that looks like on the gauge. And this is why I wanted the 25 ohm dummy load. It puts the needle right in the middle of the gauge. Now, it might not be the same on yours, but it'll be somewhere in the middle. The interesting thing is that that signal is not linear, so you can't really divide the difference between 10 ohms and 73 ohms and come up with 25 ohms. Through trial and error, I figured out 25 ohms works pretty good. It's close to the middle. I'm also thinking if you have just one dummy load, it should be 25 ohms. That'll tell you if your gauge circuit is in the ballpark. It's pretty much all you need to know. Unfortunately, I don't have an oscilloscope to check the voltage regulator output waveform. That's really the only way to confirm this output is healthy. But if I did, it should look something like this. It's a trace of 12 volt pulses at a 50% duty cycle rate. Duty cycle is the percent pulse width over the period. As we can see here, a 50% duty cycle repetitiously turning 12 volts on and off over time results in a 6 volt average voltage. My dummy load test results imply the voltage is within reason, but naturally I really wanted to measure it somehow. So I've switched this over to volts, DC volts, and I'm going to just, can't do this with one hand, hang on. There, I hooked the red lead to the sensor wire, temperature sensor wire. And the key is turned on, so there's power on it. And this is what it does. The reason it does that is because this voltage signal is actually pulsing on, off, or on and then some lower level, which I don't know. The only true way to read this is with an oscilloscope where you can actually see the trace. But I'm going to try my Klein tools meter. That actually has a duty cycle measurement and a percent duty cycle, so we'll see what that says. That'll be interesting. So I put this up here on Hertz measurement. And that's all over the place. It can't really read the frequency. But let's select percent. Or if I do this. Yep. So that's about a 20% duty cycle then. So the voltage coming from that little voltage regulator is actually pulsing at about a 20% duty cycle, which means that the 6 volts or 5 volts is only on 20% of the time, and it's off 80% of the time. Let's try voltage.
That's AC volts. Auto.
Like the Flux meter, DC volts is all over the place as expected. This pulsing voltage can't be directly measured with a digital meter.
How about... No, that's DC auto. How about DC max? Maximum right there, 5.3 volts. 5.63. For some reason it's capturing it now, that's good. 5.77 maximum DC voltage. Ooh, 6.44. That's interesting, and maybe that little voltage regulator is unstable, possibly.
So there's a discrepancy here that can only be solved with an oscilloscope. If the duty cycle is 20%, as the meter indicated, the average voltage should be 2.4 volts. But if that's the case, the gauge wouldn't be reading such reasonable levels. Unfortunately, that's going to remain a mystery for now. But so far, we found the circuit to be okay, and we still haven't identified the problem with the temperature gauge.
Temperature gauge hasn't come up yet. Who knows if these are working or not? Okay, I have the red lead on the terminal, the stud on top of the temperature sensor. The black lead is on the ground, and they're coming over here to the ohm meter now. This is cold. So the engine hasn't been running a couple days and it's reading 399 ohms, 398 ohms. At first I thought that was surprisingly high. But then I checked a brand new temperature sensor I got. So I just got this one brand new the other day. And that's reading 337 ohms. Well, I guess it is 60 ohms lower, and we know that makes a big difference, so we'll have to try that out at some point. So this is a very old temperature sensor I got from, it was a 68302 I used to have. I actually just removed it from the intake manifold that I still have. And that's reading 284, 285. It seems to be climbing. So that's not bad. So by comparison, that's still lower than the other one. So the temperature sensor right now is around 62 degrees. I'm going to warm the engine up. I'm going to take the car outside, warm it up, check the temperature, and then check the resistance on it. We'll see what happens. Degrees, 177 degrees.
The resistance of the warmed up sensor is lower than 73 ohms, so the gauge needle should be to the right of the cold line. But as we've seen, it never is. So what if the resistance through the gauge wiring is too high? I used a clip lead to connect the sensor to the worn out old plug-on wire connector, and just to make sure, I jumpered another chassis ground connection. That made a significant difference. This is more than I've ever seen this gauge move. It looks like I should look for other sources of excess resistance in this old car wiring. I figured I might as well start with replacing the temperature sender. The new one has lower initial resistance, so that should help. I knew the temperature sender is below the water line in the radiator and intake manifold, but I didn't want to drain the radiator just to swap out the temperature sender. I was hoping the closed cooling system would hold the liquid in, kind of like putting your finger over the end of a straw. It didn't quite work that way. I wrapped this rag around here because I'm sure that the antifreeze is going to start coming out through this hole, because I didn't drain it at all. Here we go. I'm hoping it will be somewhat limited, but it looks like it's not. It's coming out like a geyser almost. Alright. That wasn't actually too bad. Close it off as quickly as I can then. I lost a little bit of antifreeze. And soak it up. But saved a lot of time. I cut that little connector off of here. Just want to clean these copper wires up a bit if I can. They're very, well, I won't say very, they've got quite a bit of oxidation on their surface. They're somewhat oxidized. I want them nice and shiny like that to reduce resistance. Okay. I replaced the push-on connector with a ring lug of the perfect size. So I'm going to fill that lug, that crimp lug, with a little bit of solder. If this soldering iron will heat it up enough. Which is in question. Oh yeah, there it is. Whoops. That should do it. Some people might disagree with soldering this, but the crimp makes the bond mechanically strong, but not electrically strong. The solder will tin the copper and prevent it from oxidizing. And since it's filled, all the air gaps in there are filled with solder,
it's not going to be subject to moisture or air. And I'll finish this off with a little bit of shrink tubing on there. Ow. Okay, nice. I'll just let that cool off now. So I found two of these little brass nuts. They have a little shoulder on them. It's very slight, and they're the correct size for the stud on top of the sensor. I already put one on there. I gave them the Scotch-Brite treatment so they'd be nice and clean and shiny. And that's a good connection right there. Nice tight connection. Okay, so this red lead from the, or I should say to the sensor there, I'm pretty sure comes in through this connector. This is a bulkhead connector in the firewall. And it probably, and I'm going to guess it hasn't been disconnected, possibly for 58 years. But I'm going to pull this apart, hopefully without doing any damage. And those pins don't look bad. They're not really that oxidized. But I'm going to clean them. And I'm going to clean these sockets out in here. The one thing I wanted to do is check which one of these is our power supply, our 6-volt signal. So I'll connect this to a good ground. And this is one of those voltage test lights that has a little voltmeter in it too, a little digital voltmeter. So let's see what we have in here. That one is pulsing. So I got lucky and hit the right one on the first guess. What's this one got on it? This one should have 12. That one's pulsing. Okay. Maybe that's for the oil sender. Alright, let's see, what's this? Alright, this one here, I don't know if you can see it on the camera. It's reading 12.4 volts, solid. This one is nothing, it could be a ground. This one is pulsing. So that's probably our power supply or our ground wire coming from the meter, from the gauge. This one's pulsing, I can't read it. And this one's nothing. That's nothing. And that's pulsing. So two of those are pulsing, so I'm guessing that's the temperature sensor and the oil pressure sensor. So I'm using CRC's contact cleaner, precision cleaner solvent, leaves no residue, for electrical and electronic grade. Unfortunately, there's not much left in here. Wish I had more, but what I'm going to do, spray it in there. I'm spraying it on good old-fashioned pipe cleaner here. I'm going to run the pipe cleaner in and out of these sockets. And it's coming out a little dirty. I guess it doesn't take much. I'll hit it again. Well, that was much, but okay. I gave it much. And then with a clean dry one, I'll just go in there and I don't have a tiny round brush that would get in there, so I'm using pipe cleaners. Pipe cleaners look like this. They're literally for cleaning old-fashioned tobacco pipes. The original Ream and Clean bristle, extra rigid. It cleans, it scrubs, it absorbs. Bryn Mawr brand. That's for the old guys who used to smoke pipes with tobacco in them. Okay. Now this side, a couple sockets there. Need to be cleaned out. Oh, that's dirty. I'm going to need to get a new can of that stuff. Okay, that's pretty good. Now I actually want to try to clean these pins if I can. Maybe work them with a used toothbrush. It evaporates very quickly. And finally, there's two pins on the connector here itself on the firewall, and they actually look pretty bad. I hope I have enough contact cleaner to do something with those. Seems like it's empty. Darn it. It's empty. I'll just brush it with a mostly dry brush then. Mostly dry, soft bristle toothbrush. I don't want to get too aggressive with these. That should help. Some people might think it would be a good idea to put dielectric grease on these. I don't. Dielectric is an insulator, so if you get grease inside those pins, you could be adding resistance to the connection. Yeah, it might protect them from further oxidation in the future, but it could create more resistance in the circuit right now. And I'm looking to get rid of that. And I don't know if you can see it, but there's a bit of bare wire right here. Someone had tapped into a 12 volt line there with a 5 volt or a 5 amp fuse for this little oddball security system that's in this car. I'm going to leave it on there for now. I untaped it just to see how they connected it. It's just bare wire wrapped on bare wire. No solder, no compression lug, and it was wrapped with tape. I'm going to leave it there for right now. I haven't decided what I'm going to do with it in the long run. So now I'm going to start it up, take it outside, let it get warmed up, and see what the gauge looks like. I'd say that made a bit of a difference. I'm a little more comfortable with it in that location, or in that position. Basically pointing almost toward the T in temp. That could be a good place for it to run a normal temperature. It's warmed up now, that's for sure. It's 158 degrees up there. So I think we found a solution. This is better than it's ever been. I just drove it around the yard a little bit, and that's where it ended up. So even slightly higher than it was before.
Thank you for watching. Please take a moment to like and subscribe.